This is my Precalculus course. Today you're going to prepare for the second half of the final test. The second half is obviously going to cover the material that you were tested on from test number 3 and number 4. And you're allowed a calculator, and you can use it for graphing for this this part 2 of the final test. And remember, these practice exams that we're going to do are the minimum that you need to prepare. So as usual, we're going to do a practice exam together right now, version 1, and I'm going to give you a practice test for homework. So these practice tests are designed to be a starting point for you, to help you study. But if you want to get a really good score, you need to go back and review all of the material that we learned, not just these practice tests. So the practice tests are a starting point. They're the minimum that you need to prepare, but they don't guarantee that you're going to get an A on the test. I want you to try number 1. If you get stuck, that's okay. But if you do get stuck, that tells you that you need to do more of these types of problems. You don't know them well enough. If you can do this problem really well, then that means that you don't have to spend so much time studying these types of problems. So again, that's the purpose for this test. It's to help you study. And so I want you to attempt this problem on your own. Don't just watch me do it. I want you to see if you can do this on your own. So go ahead and try number 1. When you come back, we'll do it together. Okay, we're back. So we're going to move 2 units to the left on the real axis, and then we're going to move 1 unit up because the coefficient of I is 1. So that's what it means to graph a complex number. I know that's a strange thing, but mathematicians do that for various reasons. So if you got that right, good job. Go ahead and try number 2. When you come back, we'll do it together. Alright, we're back. So we're going to find the difference quotient. I'm going to label that as DQ. You don't have to write DQ, but it's probably good to label what you're finding. The difference quotient is f of x plus h minus f of x over h. You need to have this formula memorized. You're not allowed to, look at your notes. You need to have this memorized. No notes on the test. No internet, no nothing. You need to do this from memory. Okay, so first we're going to find f of x plus h. So f of x plus h is this expression here, except instead of x, you write x plus h. So that is f of x plus h. Then we're going to subtract f of x, which is the exact expression that we were given. No difference whatsoever. So that is f of x, and then we're going to divide all that by h. So that is the difference quotient. Of course, you don't have to use these colors. That's just to help you figure out what it is that we found. So if you got that right, excellent. Okay, go ahead and try number 3. When you come back, we'll do it together. Alright, we're back. So the average rate of change between x equals 1 and x equals 3 is the slope of the purple secant line that goes through those points on the red curve. So you can use whatever notation you want, but I'm going to write m average. That means we're finding the slope, which is slope of a line, which is usually written as an m, but we're going to call it the average rate of change. So I'm writing an AVE. You don't have to do that, but The slope of a line is simply the change in y values over the change in x values. And because we're using functions here, we can call y2 f of x2, and we can call y1 f of x1. Now x2 is 3 and x1 is 1, and f of 3 is just this expression with 3 plugged in, so 3 squared, and f of 1 is this expression with 1 plugged in, so 1 squared. So 3 squared is 9, 1 squared is 1, 3 minus 1 is 2, so we're left with 4. Y increases by 4 units for every 1 unit that x increases. That's the average rate of change of the function. The function is the red curve. So if you got that right, good job. So that's a definition. That's the definition of the average rate of change in that interval. So I want you to try number 4, and when you come back, we'll do it together. Okay, we're back. So we have rectangular coordinates here, x and y, and we want to convert to r and theta. That's what it means to convert to polar coordinates. So I'm going to count 7 units to the left and 4 units up. Okay, so we have x and y. We don't want x and y. We want r and theta. But we can find r and theta using x and y. So how do we find r? Well, we know that x squared plus y squared is equal to r squared. So negative 7 squared plus 4 squared is equal to r squared. So we have 49 plus 16 is equal to r squared. And so r squared is equal to 65, and r is equal to plus or minus root 65. Now, normally r is not allowed to be negative. When you're calculating the values of trigonometric functions, r is defined to be positive. But when you're graphing points using polar coordinates, r can actually be negative. But we don't know if we're going to choose positive root 65 or negative root 65. We won't know that until we find theta. So how do we find theta? Well, we know that tangent theta is equal to y over x. Now, what you might be thinking is, how do I know these formulas? Well, you need to memorize them. You need to have those memorized for the test. And you should already have them memorized. I mean, we learned this in my trigonometry course, in my geometry course, and so on and so forth. So tangent theta is equal to y, which is 4 over negative 7. And we want to find theta, but we can't, because this is not a special ratio. It's not a recognizable ratio, so we need to use the calculator. So remember, in your calculator, we're going to enter tangent inverse of negative 4 over 7. So you want to make sure that you're in degrees. You can use radians, I guess, but it doesn't tell us to use, well, actually it does tell us to use degree units, so you want to make sure you're in degree units. So push the mode button on your TI-84 Plus, make sure you're in degree units. Then you're going to push the blue second button, and then the tan button, and then the negative symbol at the bottom right with the parentheses around it, and then 4 divided by 7, and then right parenthesis. And so we get approximately negative 29 point, and it says round to the nearest tenth in purple there, so negative 29.7 degrees. So now we can figure out if we're going to use positive root 65 or negative root 65. So let's say that we're going to use positive root 65. So that means that we count out on the x-axis root 65, and then we're going to rotate negative 29.7, which is going to get us here. Is that the right point? No, that's not the right point. The right point is up here. That's where we need to be. So obviously using positive root 65 with this particular angle is not going to work. Now what if we use negative root 65? Well, then we count out root 65 on in the negative direction, and then if we rotate negative 29.7, then we rotate clockwise and we get to our point. So that tells us that we need to use negative root 65. So in polar coordinates, our point is negative root 65, comma, negative 29.7 degrees. So if you got that right, excellent. Now, do you have to round off for this number? Should we use our calculator for that number? Well, no, because we can just write the exact number. So we can just leave it as negative root 65. If you want to round off, that's fine, I guess, but I'd prefer just leave it as negative root 65. Okay, so go ahead and try number 5. When you come back, we'll do it together. All right, we're back. So we're going to count root 2 to the right and then rotate 225 degrees. So that gets us there, and the angle is 225 degrees. So in order to understand what's going on here, I'm going to make a triangle, and we're looking for x and y. That's the whole point of this. We want to find x and y because we're converting to rectangular coordinates. These are polar coordinates because we have an angle here and we have r. Now the reference angle, the green angle, is going to be 45 degrees, and what that tells us is, well, we don't even need a calculator for this because this is a special angle. We have a 45, 45, 90 triangle, and remember, I think we used B as our letter there, so this is the 45, 45, 90 relation in terms of the sides. So if B is 1, then you get root 2 as the hypotenuse. So that means that the sides are 1, but x has to be negative 1 and y has to be negative 1 because we're going to the left and down. So that's pretty much it. We didn't really need to do much, or we didn't need to show much. I mean, we showed our picture. That's pretty much it for number 5. So if you got that right, excellent. Okay, go ahead and try number 6, and when you come back, we'll do it together. All right, we're back. So if you recall, we'll draw any triangle, and if this angle is theta and this is r, the hypotenuse is r, and this leg is x and this leg is y, then obviously cosine theta is equal to the adjacent side over the hypotenuse. We learned this in my trigonometry course and also my geometry course. So if that's true, then that means r times cosine theta is equal to x. You just multiply both sides by r. So you already have this memorized. It's not like you have to spend a lot of time to memorize this. So we're going to replace x with r times cosine theta. Why are we going to do that? Well, because we want to switch from x and y to r and theta. Using the same definition, or the same trigonometric definitions, we have r sine theta for y. Again, replacing x with r cosine theta and y with r sine theta. Okay, so we're going to use exponent rule number 3. That becomes r squared cosine squared theta plus r squared sine squared theta. And then we're going to divide both sides by r. Well, maybe we can just factor out r. You can do this a lot of different ways. I'm going to just factor out r. You could just divide both sides by r also. Then I'm going to factor out r squared in the right side of the equation. Now, it's very important to remember that this expression here is an identity, a very important identity. That expression is just 1. As long as the angle is the same, then that expression is just 1. And again, you don't really have to factor out the r's. You can just divide by r, and as long as you understand how to cancel things out, you can do it that way. So if you divide both sides by r, you would just get cosine theta plus sine theta is equal to r times cosine squared theta plus r times sine squared theta. Okay, so now we're going to go ahead and divide both sides by r, and we're left with the same thing that we got by dividing in the first step. So that is the equation in polar form. Now, technically, you would have to check to make sure that these graphs tell you the same thing, because sometimes they're not the exact same graph. You have restrictions in one graph or the other graph, but I'm not going to give you problems that are that difficult. It's very challenging to figure out the restrictions. I'm just going to give you problems where there are no restrictions that you have to worry about. So if you got that right, excellent. If you're a little rusty on that, again, that's okay. That's the purpose of this practice exam, is to help you figure out what you need to study and what you do not need to study. Now, you might be given a problem like this, and you might be asked to go in the other direction. So be aware that that might occur on the test. Okay, go ahead and try number 7. When you come back, we'll do it together. Okay, we're back. So, isn't it true that f of x, we're told, is equal to negative 5x squared plus 11x minus 10? We're told that. But if that's true, then that means that f of k is equal to negative 5k squared plus 11k minus 10. Because we're just plugging in a different number, or we're plugging in something different rather than x. We're just plugging in k. Now, k is an exact number. X is a variable. K is a letter that represents an exact number, whereas x is a letter that does not necessarily represent an exact number. It's kind of hard to wrap our brains around. But now, what this information tells us is that if k is your input, negative 5 is your output. So if k is the input, the blue output should be negative 5. So what that means is that we can rewrite the equation and say that f of k is negative 5. Because that's exactly what it says up here. F of k is negative 5. So now we have a quadratic equation, and we can't solve quadratic equations. unless we put them in standard form. So I'm going to add 5 to both sides. And then we get the standard form. And what you'll find is that this is not really easily factored. So we're going to have to use the quadratic formula. Don't be afraid of the quadratic formula. It's nothing to be afraid of. Okay, so now you might be wondering, well, how did I know to use this? Well, you can use this anytime you want to use it. It works in every single case. But if you try to factor this and you find that it's very difficult to factor, then just retreat to this. There's no reason that you can't just go straight to the quadratic formula every time you want to solve a quadratic equation. Is that clear? So whenever you have a situation where there's a coefficient here, you might want to just go to the quadratic formula, because it complicates things when you have a coefficient on the squared variable term. So b is 11. And a is -5. And c is also -5. Okay, so now we just have to simplify. So we have -11 plus or minus root 121 minus 100, it looks like, all over -10. So let's make sure that we have everything written down properly. Looks like we do. So k is equal to -11 plus or minus root 21 over -10. And notice that we have a negative here and here. Mathematicians like to simplify that a little bit, because if you multiply both sides of the fraction by -1, we get this simpler expression. But because this is a plus or minus symbol, when you multiply by -1, it doesn't really change it. It doesn't have any effect that we need to consider, really. So there you go. Those are the two solutions. Those are the two values of k that would make this function equal to -5. So have you got that right? Excellent. Okay. Try number 8. When you come back, we'll do it together. All right, we're back. So the easiest way to do this is to let x equal t and to let y equal log base 2 of t plus 3. Okay, now t cannot be any value that is -3 or less than -3 in this situation. But we don't really need to write that. We can just assume that that's implied. I'm not going to make you write that. So that's the easiest way to do it. That's not the only way to do it. You could let y equal t, but then x would equal 2 to the t minus 3. You'd have to solve for x, so that would require more math. Go ahead and try number 9. The first, well, there's 4 parts for number 9. When you come back, we'll do it together. Okay, we're back. So we're writing the inverse relation, and that just means that you flip the x and y values. So very easy. That's a very easy problem. Now we're going to find the inverse graph. So recall, to find the inverse graph, what you do is you reflect the graph across the y-axis, and then you rotate 90 degrees clockwise. So if you do that, you end up with this weird shape looking something like that, and it doesn't have to be perfect. Notice that my graph is not perfect, but it's about right, so that's good enough for credit. You don't have to be some incredible artist. Okay, so now remember, when you find the inverse equation, you simply switch the x's and the y's. So we have cosecant squared y minus 1 is equal to x. So you just switch the x's and the y's. That's the inverse relation. Now, if you're trying to find inverse functions, it's a little bit more complicated because you have to solve for the output. When you're dealing with relations, we don't have to solve for the output. Even though this is actually solved for the output, but this is not solved for the output. So here we're going to do the same thing. We're just going to change x to y and y to x, and you're done. So as you can see, that's very easy. So if you got that right, excellent. Go ahead and try number 10, and when you come back, we'll do it together. Okay, we're back. So you don't necessarily have to use your calculator to graph this, but it's probably a good idea. You want to push the mode button and then go down to para or pair. Change from function or pole mode to pair. So that means we're going to parametric mode, and then you're going to push the y equals button at the upper left, and then you have your parametric equations. So you're going to enter those in. x1t is going to be square root t, and you want to push the x comma t comma theta comma n button, which will give you a capital T. So what you should have in your TI-84 Plus is this. That's what it's going to look like. It's using a capital T instead of a lowercase t, but the parameter is usually going to be a lowercase t in most textbooks. So then push the down arrow key and then enter the x comma t comma theta comma n button right under. That button's right under the mode button, if I didn't tell you that, plus a 1, and there you have your parameters. So or your parametric equations. But then you want to go to the window, and you want to make sure that you define the values of t. So let's let t go from -10 to +10. And the t step, let's change the t step to 0.1. The calculator's gonna graph a point at intervals of 0.1 units for t. If you make the step too big, then your graph will be jaggedy. It won't be smooth. So x minimum, let's make that -5, and x maximum +5, y minimum -5, y maximum 5. Then you're going to push graph, and we'll see what this looks like. So that tells you what the graph should look like, but we have to actually do this to show that we know how to do it. So notice that we can't choose any t values that are less than 0, because then you have imaginary numbers. That's why our graph is only half of the parabola. So we're going to choose 0, x is equal to square root 0, and y is equal to 0 plus 1. X is equal to 0, y is equal to 1. You don't have to show all of this work because it's kind of obvious what the values are going to be. So 0, 1 is right about there. Alright, let's choose another t value. Let's choose 1. So then x is equal to square root of 1, and y is equal to 1 plus 1. So x is equal to 1, y is equal to 2. So we have 1 comma 2. So we're going to go out 1, up 2. And we need to find 2 other points. So let's choose t is equal to 4. I'm trying to avoid irrational numbers. So x is equal to the square root of 4. Y is equal to 4 plus 1, so x is equal to 2, y is equal to 5. Again, you don't have to show every step of this math. You don't necessarily have to show all of this stuff. You can do it in your head. You don't have to show it on the test, because this is just basic mathematics. So now at this point we're kind of forced to use a value that's not going to be pleasant, because we don't have any other values that are in the window that we can use. And I forgot to plot that point. 2, 5 is up there. So I graph that point. And so we have root 2, comma 3. And if you're not sure what root 2 would be, you can just enter that into your calculator, and it's about 1.4. So if we go out to the right 1.4, we go up 3, which should put us about there. So that's right on that curve. And then we can connect the dots. And I didn't mention this in my class, but what you can do is write arrows on the curve if you like. That shows the direction. Again, one of the things about about parametric equations is that it gives you an order in which to plot the points. So now we just have to eliminate the parameter. So we have our equations written here. I'm going to write that for you. And there's a couple different ways we could do this. But probably the easiest way is to go ahead and square both sides of this first equation. And then plug that in for t in the second equation. That's just one way to do it. Now, probably the better way to do it is to solve for t in this equation and then plug it into the other equation. So we get x is equal to the square root of y minus 1. This is actually a better way to do it, probably, because this has the proper restrictions. This has no restrictions, but I'm not going to require you to do it one way or the other. Technically, this is the whole graph. There's no restrictions on this. This is the entire parabola. Whereas with our parametric equations, we're not graphing the entire parabola, we're only graphing half of it. But again, as long as you understand that, I don't care if you write y equals x squared plus 1. Again, if you wanted to make the graphs perfectly aligned, then you would have to write x has to be greater than or equal to 0. But if you got that graph and those points and this equation down here, or the root version of the equation, good job. Okay, so on to number 11. Go ahead and try number 11. When you come back, we'll do it together. Okay, we're back. So let's see, this is kind of a tricky one here. We have a polar equation and we're going to graph it. So let's choose our value of theta. I'm going to choose 45 degrees, and the reason I want to choose that is because I know if I multiply by 2 I get 90, and 90 is a special quadrantal angle, and we don't need to really do a lot of thinking for that. We just need to remember our graph. Sine 90 degrees is equal to exactly 1. Alright? So those are your graphs, your sine and all the different graphs. You need to memorize those. So r is equal to the square root of 16 times sine 2 times 45 degrees. So r is equal to the square root of 16 times sine 90 degrees. And we have 16 times 1, and long story short, r is equal to 4, so the point is 4, 45 degrees. What that means is we're going to count out 4 units on the x-axis, and then we're going to rotate 45 degrees. So that's going to be somewhere around there, somewhere up here. Doesn't have to be an exact location. You don't have to use a protractor or anything. Okay, so we need to find some other points. So let's try theta is equal to 0. 0 degrees. Then we have r is equal to the square root of 16 times sine 2 times 0 degrees. So r is equal to the square root of 16 times sine 0, which is just 0. So r is 0. So we have the point 0, 0 degrees. So that means we have a point at the origin. And let's try to find a couple other points. Let's see. So I think we can plug in 15 degrees. Sometimes you can plug in values that are really easy, sometimes you can't. So r equals root 16 times sine 2 times 15 degrees. We have 16 times sine 30 degrees. Sine 30 degrees is 1/2. We don't need a calculator for that if you know your trigonometry. And long story short, we're going to end up with the square root of 8. And you can use your calculator for that. But we can write it as 2 root 2. So the point that we need is 2 root 2, 15 degrees. So 2 root 2, 15 degrees. So the square root of 8 is obviously going to be a little bit less than 3. That's going to be about 2.8. So we're going to count 2.8 units, 1, 2, and then rotate about 15 degrees. So it's going to get us about there. So now we can find one more point. Now we're going to graph this in our calculator because we'd be here all day trying to find points in order to see exactly what this is going to look like. But we may not be able to find values that we like between 0 and 90. So we're going to have to go up to 180 to 270. And the reason we have to skip is because r cannot be negative, because the square root of a number cannot be negative. You can't choose values of theta that will give you a negative sign value, because then we'd have a negative under the root. So let's choose some theta value between 180 and 270. So we'd like to choose values where we don't have to use a calculator, but it doesn't really matter. You can choose whatever value you want. Let's see, if we choose 225 degrees, maybe that'll give us a value. Again, you can choose 200 degrees and then just use the calculator. I think 225 degrees is going to work. So 2 times 225 degrees, that's going to give us sine 450 degrees, which is a special angle. Now, how do we know what sine 450 degrees is? Well, this is 360 degrees. That's a complete cycle. And if you go 90 more, you get to 450 degrees, and that would be 1. So that's going to be 16 times 1, so r is equal to 4, and so the point is 4 comma 225 degrees. And so we're going to count out 4 units, 1, 2, 3, 4, and then rotate 225 degrees, which will get us somewhere down here. Again, it doesn't have to be perfect location. So now we have 4 points, the coordinates of 4 points. But again, it's very difficult to see what the graph is going to be using this type of method. It's going to take forever. So we're going to push the mode button, and we're going to switch to polar mode. So go down with the arrow key after pushing the mode button and push enter on pole. Pole means polar. Make sure you're in degrees because we're using degree units. Then push the y equals button, and you're going to enter in the square root of 16 times sine 2 theta. Then you're going to push the window button, and notice we have theta minimum and theta maximum. I'm going to use negative 180 and positive 180. Hopefully that's enough. My step for theta is going to be 1. If your step is too big, then the graph is going to be too jaggedy. And x minimum, I'm going to, well, we have the graph to help us with that. So x minimum is going to be 1, 2, 3, 4, negative 5. X maximum is going to be 4. And y minimum is going to be negative 5, and y maximum is going to be 4. I'm just copying down exactly what the graph, or the window on the actual graph that you're given is. Again, you don't have to guess about how big the window is because I've got the window right here for you. Okay, so now you can see what's going on here. We've got some sort of a we've got some petals there, whatever you want to call them. So that's about as accurate as you need to get. You don't have to have a perfect drawing. So if you got that right, excellent. Okay. So on to number 12. Go ahead and try number 12. And when you come back, we'll do it together. Alright, we're back. So if we're reflecting across the x-axis, we change the sign of the y value. So we're going to have 5, negative 4, 1, negative 10, negative 40. And the x values don't change sign. Alright. And then if we're going to reflect across the y-axis, we change the x to a negative x in our equations. And we're just going to simplify a little bit. If you square a negative, the negative just disappears. So there you go. That is the equation of the relation that is reflected across the y-axis. So now we're going to reflect across the origin. To do that, you simply reflect across the x-axis, and then you reflect across the y-axis. So I've actually shown you how to do it here. Although I may not have this on the actual test, because you really should know how to do that without being told how to do it. So let me find my purple pen here. So we're going to reflect across the x-axis, which would make the triangle go down there precisely, and then reflect across the y-axis, which would make the triangle go to there. Again, your drawing doesn't have to be perfect. Okay, now we're going to reflect across the x-axis, which means that we changed y to negative y. So if you got that right, excellent. Okay. Go ahead and try number 13. It's a two-part problem. When you come back, we'll do it together. Okay, we're back. So this shows no symmetry. This shows symmetry about the origin. This shows symmetry about the origin, the x-axis, and looks like the y-axis also. So for every point x, you have another point x, or negative x, negative y. That's the origin, symmetry about the origin. For every point xy, you have another point x, negative y. That's symmetry about the x-axis. For every point xy, you have another point negative xy. That's symmetry about the y-axis. So here you have symmetry about the y-axis. You have no symmetry, and you have symmetry about the origin. So if you got those right, good. So if you need to review symmetry, you can go back and review that. If you're lost when it comes to that, well, again, that tells you something. That's the purpose of these practice tests, is to tell you where to study, what to go back and look over. Okay, so now it says that the table below has points collected from a graph that is symmetric about the x-axis. Fill the empty spaces. So if the graph is symmetric about the x-axis, then that means for every point xy, you have another point x negative y. So you have the point 10, 9. That means you should have the point 10, negative 9 also. And so on and so forth. So all we're doing is just changing the sign of the y values. So if you got that right, excellent. Make sure to double check your values. It's easy to make a small mistake when you're filling those in. You don't want to get the problem wrong because of a small mistake. Now, problem 13 has a part 3 and a part 4, so go ahead and try part 3 and part 4. When you come back, we'll do it together. Okay, we're back. So we're using this equation for parts 3 and 4. It wants to know if the graph of this equation is symmetric about the y-axis. To figure that out, we switch x to negative x in our equation, and then we ask ourselves, after simplifying this equation, if we could simplify this equation, does it look exactly the same as the original? And there's nothing we can really do to simplify it, so this is the most simple form. But does it look the same as this equation? And the answer is no, because there's a negative symbol here. It's different. So that means it's not symmetric. The graph of this equation here is not symmetric about the y-axis. So now we're going to do the same thing. We're going to figure out if the graph of this equation is symmetric about the origin. To do that, we change y to negative y, and we change x to negative x. And then we simplify. And after simplifying, if this equation looks exactly the same as the original, then that means the graph of the original equation is symmetric about the origin. So let's see what happens. We get y squared minus x is equal to cosine y. Now remember, the negative symbol disappears in cosine and secant curves, or cosine and secant functions. The negative comes out if you have a tangent or any other function. The negative comes out in front. Now again, if you want to know why that is, you can go back and look at that, but all we're doing now is just taking a practice test. We're not giving a complete instruction on that. Most students just memorize that. They don't really know why it is, although it's easy to prove that that is true. Okay, so we simplified, and here's the question. Is this equation exactly the same as the original? And the answer is no. So the graph of the original equation, the graph of this equation here, is not symmetric about the origin. So if you got that right, excellent. Go ahead and try part 1 of 14, and when you come back, we'll do it together. Okay, we're back. So it says this is an odd function. If it's an odd function, then for every point x, y, you should have a point negative x, negative y. So if we have the point 1, 2, then we should also have the point negative 1, negative 2. And so we can just fill in the table there. All right. So if you got that problem, good job. All right. Try parts 2 through 4 on number 14. When you come back, we'll do it together. Okay, we're back. So if a function is even, that means it's symmetric about the y-axis. If it's odd, that means it's symmetric about the origin. So this graph is not symmetric about anything. So we can say that is neither. And this graph is symmetric about the y-axis, so it's an even function. This is also symmetric about the y-axis, so it's an even function. And this is symmetric about the origin, because for every point x, y, you have another point negative x, negative y. So that is called an odd function because it's symmetric about the origin. So if you got that right, excellent. Now, this graph here, for example, is not symmetric about the origin, because if you choose, let's say you choose a point there, then you should have another point that's up here if you go straight across the origin. So that's not symmetric about the origin. Okay, so part 3, it says if f is an even function and f of negative 2 is 11, find f of 2. So if the function is even, that means the graph is symmetric about the y-axis. So what that means is if you have the point negative 2, 11, which is what this information tells us, because the graph of the function is symmetric about the y-axis, you should also have the point 2, 11. Okay? So what that means is if your x value is 2, then your y value is 11. That's it. So it's not a difficult problem. It's just a problem that is confusing because we're using function notation. Function notation, again, is very confusing. Okay, so if f is an odd function and f of 9 is 346, find f of negative 9. So if it's an odd function, that means that if we have the point 9, 346, which this information tells us, we should also have the point negative 9, negative 346. So if the x value of the function is negative 9, then the y value is negative 346. That's what it's asking. Okay, and technically you just want to, it's probably best just to rectangle the actual number we're looking for. I don't want to add any confusion here. Okay, so if you got those right, excellent. Go ahead and try number 15. When you come back, we'll do it together. Okay, we're back. So to figure out if a function is odd or even or neither, we simply replace x with negative x. It's that simple. Then we simplify. And if we get the same expression that we started with after simplifying, then that means it's an even function that is symmetric about the y-axis. If we get the original expression except a negative in front of it, then that means it's an odd function and it's symmetric about the origin. So that's what you need to remember. If f of negative x is equal to f of x, then it's even. If f of negative x is equal to negative f of x, then the original function is odd. That's it. That's all you have to remember. Okay, so we're going to simplify. We get x squared. Square negative, negative just goes away. And remember, with the secant function or the cosine function, the negative in the angle just disappears. So we got back to our original function. Whoops, that should be an f of negative x. Sorry. So we proved that f of negative x is just equal to f of x. So what does that mean? It means that the original function is an even function, meaning it's symmetric about the y-axis. Okay. If you got that right, excellent. Try number 16. When you come back, we'll do it together. All right, we're back. So we want f of x to be equal to h of x. We want negative 2x squared minus 4x minus 1 to be equal to negative 2x squared plus x plus 1. So now if we add 2x squared to both sides, we cancel out this term here, and we're left with negative 4x minus 1 is equal to x plus 1. Doing some basic algebra, we find that x is equal to negative 2 over 5. So for what value or values of x does f of x equal h of x? Well, negative 2/5. So if you got that right, excellent. Okay, go ahead and try number 17, and when you come back, we'll do it together. All right, we're back. So remember, the carrying capacity is that number in the numerator. This is called logistic growth. It's the logistic growth model, and the number in the numerator is always the carrying capacity. Why is that? Well, because this is a negative exponent. If you let t approach infinity, which is just a fancy way of saying let t be really big, a really big number, then this number becomes a very big negative number. If it's a very big negative number, then that means you're going to get 1 over e to some really big number here. Because a negative exponent, remember, it goes down into the numerator. And 36 is going to hang out here, or you can just put it in the numerator wherever you want to put it. So as this yellow number gets bigger and bigger and bigger, that means that this whole fraction is just going to approach 0, because if the denominator of the fraction is really big, then the whole fraction approaches 0, because e is just a constant. Raise it to some big number, you get a bigger number, and then your fraction approaches 0, and this whole term approaches 0, because a number that's very small times 36 is going to be a very small number. Long story short, this entire term is going to disappear, and you're going to be left with 99,000 divided by 1. So you don't have to think about that. You just have to memorize that this is the carrying capacity. What is the initial population? Well, that's just the population when the clock starts, when the time is 0. So you can probably do that in your head without really showing much work, but I want you to at least plug in your value so we can see what exactly we're doing. So we're plugging in 0, and I'll show you the steps here. Again, you don't need to show the steps, but I'll show you the steps required to do this, the operations, because a lot of students get confused by this. So negative 0.13 times 0 is 0. Okay, that's step number 1. E to the 0 power is 1. That's step number 2. And how do we know that? Well, that's exponent rule number, I think that's number 7, if I remember correctly. And then we have 36 times 1 is 36. And long story short, we have 99,000 divided by 37. So you can do that on your calculator. 99,000 divided by 37 is 2,675.675. And notice that it doesn't say to round off, but we can just round off to the nearest bacteria. So we can say 2,676 bacteria. So sorry that I didn't give you enough room here. I'll just move that up a little bit. So there you go. 2,676 bacteria. If you got that right, good. So for part 3, we're going to do the same thing that we did for part 2. The only difference is we're going to plug in 5 rather than 0. Now again, you use the same steps to do the math. Obviously, you're going to have to use the calculator. But you can enter this into the calculator in one step. That's the easiest way to do it. So I'm going to push the alpha button, then the y equals button. The alpha button is the green button. The y equals button is at the upper left. I'm going to press enter, and I should have a fraction template that looks like this. Then I'm going to enter 99,000, then the down arrow key, 1 plus 36. Then I'm going to press the blue second button if you're using a TI-84 Plus. Then the LN button at the middle left. So at that point, you should have 99,000 over 1 plus 36 E, and then you should have a little box there. Then we're going to enter negative 0.13 times 5, and then push the right arrow key. I always like to push the right arrow key to get out of the fraction so we can look at the fraction that we entered. So then you're going to press enter, and then you have your answer. Okay, so we get 5,002 if we round to the nearest bacteria. So 5,002 bacteria. Again, it doesn't say what to round off to, but it's obvious that we can't have a fraction of a bacteria, so we can just round up. Okay, if you got that right, excellent. I think we have one more part to this problem. Try part 4. When you come back, we'll do it together. Okay, we're back. So log base A of B is equal to log of any base of B divided by log of that same base of A. That's the change of base formula. And the change of base formula is particularly useful to us when we have a calculator that does not have the capability of computing a log that has any base. Sometimes calculators are only capable of calculating base E or base 10 logarithms. So let's say that we are in that situation, then we're going to change to log base E of 11 over log base E of 4. We're told to use the base E function. We could also use base 10 because calculators always have either base E or base 10 if they're sophisticated enough calculators. But remember, we don't do that. We don't write log base E. We write ln. Okay, so now we can use our calculators. And again, if you're using the TI-84 Plus, you can press the green alpha button. And I'm aware that the TI-84 and most calculators, most graphing calculators that are designed today, you don't have to do this. I'm aware of that. But the problem specifically tells us to do it this way. So we're going to press the green alpha button and the y equals button and enter. That gives us a fraction template. Then we're going to enter in ln 11, down arrow key, and then ln 4, the right arrow key, and then enter. So we get approximately 1.73 if we round to the nearest thousandth. So if you got that right, excellent. Okay, go ahead and try number 18. When you come back, we'll do it together. Okay, we're back. So first we need to figure out if this qualifies as a function. So we don't see any repeated x values. So that means it does qualify as a function. Now we need to see if it can be a one-to-one function. We need to see if there's any repeated y values, and there are. 46 is repeated, so that means that this is a function, but it's not a one-to-one function because there's repeated y values. Again, we need to first see if this qualifies as a function. Are there any repeated x values? There's no repeated x values. So it is a function, or qualifies as a function. Now we need to see if there are any repeated y values, and there's no repeated y values. So not only is this a function, it's a one-to-one function. Now, some people might say, wait a second, you're talking about numbers being repeated. There are numbers that are repeated. There's a bunch of numbers that are repeated. So what are you talking about? Well, they're not repeated in the same row. Okay, that's what I mean. You don't have negative 10 repeated in this same row. You don't have negative 10 repeated in this same row. So that's what we mean. Okay, so this does not qualify as a function because we have a repeated x value, 0. So we can say not a function. And we don't have any repeated x values here, but we do have a lot of repeated y values. So this is a function, but it's not a one-to-one function. So if you got that problem right, excellent. Okay, so part 2, in the following problem, f and f inverse are inverse functions. If something is called f inverse, and it's assumed that it's the inverse function, but we're just clarifying that. So if you plug in -1 to f, the f function, if -1 is your input, then 9 is your output. All right? But because f inverse is an inverse function, what that means is if you plug in 9 to the inverse function, you're going to get -1 as your output. So what this is asking us is if we plug in 9 as our input to the inverse function, what is our output? Well, obviously -1. So there you go. So is that difficult? No. Is it confusing? Yes. The notation is very confusing. Okay. On to number 19. Go ahead and try 19. When you come back, we'll do it together. Okay, we're back. So this is a two-part problem. Part 1 is to find k. And we're going to have to use our formula. So I'm just going to label that part of the problem. So this is the law of uninhibited growth or decay. In this case, it's decay. Radioactivity follows this law. So we're told that in 14 years, a radioactive substance decreases from 600 grams to 85 grams. So we can just plug in the information we're given and solve for K. So this is a very basic exponential equation. We do need the calculator to solve it, but before we use the calculator, we're going to isolate the exponential expression. It's not isolated because the 600 is next to it. So we're going to divide both sides of the equation by 600. So dividing both sides by 600, we get the following. So we have 85 over 600 is equal to e to the 14k. Now we're stuck. We don't know what to do, unless we know how to translate from an exponential equation to a logarithmic equation. So the exponent is equal to log base e of whatever's on the other side of the equation. So this is what we tell the calculator. We need to use the calculator. We need to tell the calculator what to do, but how do we do that? Well, we use this notation, logarithm notation. But actually, we don't use that notation. Whenever you have a special base, e, you use ln. So very, very important to understand that. Then we're going to divide both sides by 14. So we get k is equal to natural log 85 over 600 divided by 14. So in your calculator, you can do this in a lot of different ways. If you're afraid that you might do this incorrectly, you can enter 85 divided by 600, press enter, and then press the ln button, and then the answer button, the negative symbol with parentheses around it. Actually, the ln button, and then the blue second button, and then the answer button at the bottom right. And you can just enter ln of your answer. That's one way to do it. Again, this is assuming if you're using a graphing calculator that's a TI. The other way you can do this is you can push the green alpha button and the y equals button and then press enter. So you should have your fraction template. Your fraction template, which looks like this. Then you're going to press ln. Then you're going to press the green alpha button and the y equals button again, and then enter, and then you should have another fraction template. So you should have something that looks like this. Then 85, down arrow key, 600, and then right arrow key, and then end parenthesis, and then down arrow key, and then 14. So you can enter the whole thing in at once. Most students would probably just prefer to do it that way. But just be aware that there is an increase in the chance that you may enter it incorrectly. But actually there's a chance that might help you to enter it incorrectly, because then you can see that it's the exactly right form that it needs to be. So k is going to be approximately 0, actually negative 0.01395 9, and I'm gonna write ... because I want you to keep that in your calculator. Don't round it off. I want you to keep that in your calculator. Okay, so now we're going to step 2. Now that we've found k, we're going to use the same formula and it wants to know how much of this same radioactive material will be left if we started with the 316 gram sample and monitored it for 10 years. So T is going to be 10, starting with 316 grams. Then we have E to the whatever the K value is, which was negative 0.13959, and again I'm going to write a dot 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 because I want you to keep that in your calculator, times 10, because the T value again is 10. So all we have to do is calculate that, and then we'll be done with this problem. So again, there's a lot of different ways you could do this. If you're using a TI-84 Plus, you can enter 316, keeping that number in your calculator, and then press the blue second button and then the LN button. So you should have 316 E to the template, or to the box. Then you're going to go, you can either press the answer button, blue second button and the negative symbol at the bottom right, or you can press the up arrow key and then highlight that number that you have in your calculator and press enter, and it'll actually throw it in there. So that's a very useful tool to have. So at this point you should have negative 0.13959 dot dot dot, and then times 10 and then enter. So times 10, and then you should have your answer. So we get 78 grams, approximately 78. It doesn't say what to round off to. So actually we should probably, given that we're dealing with radioactive substances and we're dealing with a very small amount, we can just round to the nearest 100th place. Okay, so if you got that right, very good. Now again, it may not take you this long to do this problem because you don't have to explain it to somebody. You just have to do it. So this is taking longer than it would take probably for you to do this on your own. So just be aware when you take the test, you don't have to go this slow if you don't want to. Okay, so go ahead and try number 20, and when you come back, we'll do it together. Okay, we're back. So we're going to find the inverse function. And to do that, we first change f of x to y because that just makes it easier to deal with the algebra. Then we're going to change, we're going to switch the x and the y values. So we're going to change y to x and x to y. Then we're going to solve for y. So we're going to square root both sides, and whenever you square root both sides of an equation, you have to write a plus or minus. And then we have y is equal to plus or minus root x plus 1. Okay, and so this is our inverse function, but there's a problem. So in order to demonstrate the problem, let's graph the original function. The original function looks something like this. Now, how did I know that? Well, because if you have your parent function memorized, this is the parent function. We know that looks like this, right? If you replace x with x minus 1, remember we learned in my intermediate algebra course that that's just a transformation. That means you just move the graph 1 unit to the right. So that's how we know the graph looks like that. Again, transformations are a very powerful way to help us graph. Transformations used with the library of relations or library of functions. Okay, but notice that this is not a one-to-one function, because if you use the horizontal line test, you can see that it touches the graph more than once. So what that means is that the inverse graph is not going to qualify as a function. Let's verify that. So if you want to find the inverse graph, you reflect across the y-axis, and then you rotate 90 degrees to the right. And you can see that the inverse graph doesn't pass the vertical line test, so it's not a function. So what do we do here? Well, we have to restrict the graph. Let's take the bottom part off. Okay, so that yellow part, we're cutting it off. So what that means is that our inverse function, which we can now call f inverse of x, is positive root x plus 1. Now we could have erased the other part if we chose to, but I'm just choosing to erase the negative version of that root x. And so that is the inverse function. And we can verify that the negative root x plus 1 is the yellow part by simply plugging in values. So now, to make sure that these two functions are perfectly matched inverses, we need to go back to the original function and erase the yellow part of the graph. So to do that, we're going to write a comma and then say that x has to be greater than or equal to 1. So that's technically part of the answer. Now we don't have to say that x is greater than or equal to 0 because that's kind of implied. You can't have a negative number in the root. So if you got that right, excellent. Go ahead and try number 21, and when you come back, we'll do it together. Okay, we're back. So first step is to now with these problems, by the way, you don't have to worry about this situation. If you ever do have to worry about this situation, I'm going to tell you about it. That's all this information here. But in these problems, you don't have to worry about restrictions on the graphs. So step number 1 is to change f of x to y, just so that the algebra is easier for us. Step number 2, switch the x and the y. Step number 3, solve for y. So we're finding the inverse function. So we're going to add 3 to both sides. Then we're going to divide both sides by 4. And at this point, we're stuck. We don't know what to do, unless we know how to translate from an exponential equation to a logarithmic equation, which is just something that you memorize. Y is equal to log base 10 of x plus 3 over 4. That's it. But we never write log base 10. When we have that special base, we just write log. So you can write base 10 there, but it's just never done. So now we're at the last step, step number 4, where we change y to f inverse of x. And there you go. Okay. So that's the inverse function. So if you got that right, excellent. Go ahead and try number 22. Do the same thing for 22. And when you come back, we'll do it together. Okay, we're back. So step number 1, change f of x to y. I'm also going to change ln to log base e of x, just so we can see what's going on. Step number 2, change y to x and x to y. Step number 3, solve for y. Subtract 4 from both sides. You don't have to show every algebraic step here. Multiply both sides by 26. Now we get 26x minus 104, if I did my math correctly. And at this point, we're stuck. There's nothing that we can do. We don't know what to do, unless we know how to translate a logarithmic equation to an exponential equation. The base is e. That's always the little subscript number. The exponent is whatever the logarithm is equal to. And the logarithm is equal to this, so that's the exponent. And whatever is inside the log function goes on the other side. So, and you can write it in the other order if you want. You can write the y on the other side of the equation. It really doesn't matter. Now, you might be wondering, can I just leave this as 26 times x minus 4? And the answer is yes, you can if you want to. It really doesn't matter. So you can write 26 times x minus 4 if you want to there. So now we're on the last step, step number 4, which is to change y to f inverse of x. So there you go. That is the inverse function. I'll move this down a little bit. If you got that right, excellent. Okay, on to number 23. Go ahead and try number 23. When you come back, we'll do it together. Alright, we're back. So in order to verify that these are inverses, we're going to find f of g of x, and we're also going to find g of f of x. So what this means is that we're plugging in the g function into the f function. So what that means is we're going to write f. This is f, the f function, right? But instead of x, we're going to plug in the g function. So now when you multiply these, the 2's cancel out, and you're left with x plus 3 minus 3, and the 3's cancel out, and you're left with x. So that proves that they're inverses. But just to be thorough, most textbooks will ask you to find g of f of x also. We're going to plug in the f of x function, which is 2x minus 3. And by the way, this step here is not really necessary. It's just done to kind of help you understand. It may help you, or it may just make things more confusing. But you don't have to write that step. So now we're going to write the g function, which tells us to plug in something and add 3 and then divide by 2. Isn't it true that this is the g function? Well, we're just plugging in f inside that function. So we're plugging in 2x minus 3. You don't really have to use parentheses. But the parentheses just help us to see that we're putting that inside that function. Okay, so now we're going to combine the 3's first, and then we end up with 2x over 2. Cancel out the 2's, and you're left with x, so that proves that the functions are inverses of each other. Alright, again, if you get x, then that means one function does the opposite operations as the other functions in the correct order. Alright, so if you got that right, excellent. If you want to, you can write Yes. Okay, so number 24, find the intensity of sound required to produce the following decibels. Now, you can't do this problem unless you have the formula memorized for the loudness of sound, and if you don't have that formula memorized right now, that's okay, but for the test, you need to have that memorized. So try number 24, and if you forgot the formula, well, again, that tells you that you need to remember it. So try number 24. When you come back, we'll do it together. Okay, we're back. So the formula, if you forgot it, and again, that's okay if you forgot it, is 10 times log of 10 to the 12th times x. That's just the definition for the loudness of sound. Now notice that there is no base here for the logarithm function. Why is that? Because remember, whenever you have a base 10 logarithm, the base is not written, but I'm going to write that base in just so there's no confusion, so that we know exactly what the base is. So I wrote this there. Now we're told that the decibel level is 60. We have 60 decibels. So I'm going to enter 60 for ln of x. And what this problem is asking us to do is to simply solve for x. So what we have here is a very basic logarithmic equation. We need to isolate the logarithm. We need to get the green part by itself, and it's not by itself because the purple 10 is next to it. So we have to divide both sides by 10. You don't have to show this algebra. I'm just showing you the algebra so there's no confusion whatsoever. When you take the test, that is, you don't have to show that algebra. So now we're left with 6 is equal to log base 10 of 10 to the 12th times x. And at this point, we're stuck. We don't know what to do, unless we know how to translate a logarithmic equation to an exponential equation. The base is always the little subscript. The exponent is whatever the logarithm is equal to. And whatever's in the log function, that goes on the other side of the equation. Okay. Well, now we're looking for the intensity of the sound, which is x. So we need to divide both sides of the equation by x to the 12th. And again, you don't need to show this division. You can just show the result of the division, because again, this is precalculus. You don't need to show that basic stuff. But just to avoid any possible confusion, we're going to show it. Here we have to use exponent rule number 2, which tells us that that's equal to 10 to the negative 6 power. Because remember, when you're dividing powers, you subtract the exponents. And the intensity is measured in watts per square meter. So there you go. That's the answer. So if you got that right, excellent. Now you could write 0.0000, a certain number of zeros, and then 1. That's another way to write it. That's fine if you want to do it that way. Okay, last problem. On to 25. Go and attempt number 25. Notice it says using radian units. So you need to push the mode button on your TI-84 Plus or whatever TI you're using, or whatever your calculator you're using. You need to go to the settings and change to radians. Also, we're going to graph a polar equation, so make sure that you're on polar mode. In the pushing the mode button, you have function mode, parametric mode, polar mode. Make sure you're on polar mode. So try number 25. When you come back, we'll do it together. Okay, we're back. So we can start by going ahead and graphing this in our calculator, because we're going to have to eventually anyway. So push the y equals button, and then press clear to get rid of any previous equations. Press the green alpha button, then the y equals button, then the enter button. So you should have a fraction template at that point. 2, down arrow key, 1 plus sign, then the x comma t comma theta comma n button for your variable, then the right parenthesis, and then the right arrow key. So we have 2 over 1 plus sine theta. Now you need to push the window button. Okay, so in my calculator it says negative 180 and positive 180 for theta minimum, theta max. That's not going to work because we're in radian units. So instead of negative 180, let's enter negative pi. Push the blue second button and then the upside down V button to get your pi. Then press the for theta max, blue second button, and then the upside down V button at the upper right or middle right. Enter. So you should have negative 3.14 blah 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 for a theta minimum and positive 3.14 blah 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 for the theta maximum. Your step cannot be 1 because we're not in degrees. So let's make the step 0.01 because we're in radians. It's just not good enough to have a step of 1 because our graph's not going to look right. We need a smooth graph, so we're going to choose a step of 0.01 for theta. And you don't have to guess about your window. We have a negative 5 for the x minimum, positive 4 for the x max, positive 4 for y max, and negative 5 for y minimum. Again, you don't have to guess. So push the graph button, and let's see what we get. So it looks like we have a parabola. Just waiting for the computer to graph this. And yes, we do have a parabola. So now we need to actually find some points. So let's choose a theta value, and we want to stick with the easy values if we can. So 0 radians is an easy value, so 2 over 1 plus sine 0 radians, sine 0. Remember your sine curve. That tells us what the values of the trigonometric or the sine function is when you have a quadrantal angle, so or a collapsed triangle. So sine 0 is just 0. So r would be 2. So our point is 2, 0. So I'm going to count out 2 and then rotate 0 radians. All right. And now what can we choose? Well, let's choose pi over 2. Theta is equal to pi over 2. So r is equal to 2 over 1 plus sine pi over 2. Pi over 2 is the same thing as 90 degrees. That's here. So the value of sine would just be 1. So we have 2 over 1 plus 1. And that would obviously just be 1. So r is equal to 1. The point we're looking for is 1 comma pi over 2. So I'm going to move out 1 on the x-axis, then I'm going to rotate pi over 2 degrees, which is 90 degrees, and I get that point there. So again, we're trying to stick to values of theta that make it easy for us to calculate. Now we can't use negative pi over 2 because that would give us a value of negative 1 for sine, and then we'd have 0 in the denominator of this fraction, so we can't do that. What about pi? Maybe we can use pi. Looks like that would work. So if theta is pi, we have 2 over 1 plus sine pi. Now again, picture your sine curve. Sine pi is here, so that means the value, the y value is 0. So sine pi is 0. So that means our r value is 2. So our point is 2 comma pi. Okay, so we're going to count out 2 units, then rotate pi degree, or pi radians, that is. And at that point, we have enough information to really graph this curve, but we're asked to find 4 points, so we're going to find one more. Let's see, we cannot use 270 degrees, which would be 3 pi over 2, because we get 0 in the denominator again. We could just use maybe pi over 6. It's not as easy as a value as the other values, but it's fairly easy to work with what we're going to get if we plug in pi over 6. Pi over 6 is 30 degrees. Again, pi represents 180. Divided by 3, that's obviously 60. Divide 180 by 2, that's obviously 90. Divide by 6, that's obviously 30. So 180 divided by 4 is 45. This is not difficult. So we get 2 over 1 plus 1/2. Now you might be thinking, how in the world did I get 1/2? Well, again, that's just basic trigonometry. So if your angle is 30 degrees, that's pi over 6, then you have a 30, 60, 90 degree triangle. This side is well, you can call it whatever you want to call it, but b, this side is b root 3, and this side is 2b. Sine is the opposite side divided by the hypotenuse, which is b over 2b. b's cancel out, you have 1/2. That's just basic trigonometry. So we have 2 over 1 plus 1/2, which is 3/2. Now again, trigonometry is a prerequisite for this course. That's why you have to take trigonometry before taking this course. You're expected to know that stuff. Okay, so now there's a lot of different ways to deal with this, but most students like dealing with it in this way. So simplify and you get 4/3. So our point is 4/3 comma pi over 6. So count out 4/3, which would be about here. Rotate pi over 6, which will give us to about there. It doesn't have to be perfect. And we're ready to connect the dots. Again, your graph doesn't have to be perfect. So there you go. There's the graph. There's the points. We want to rectangle all of our points because those points are part of the answer. So if you got that right, excellent. So that was the practice test. This test was, I would say, easier than the previous half, because the previous half covers more classes, whereas this half covers not so many, not quite as many. So if you got that right, good job. Okay, so that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework and to study for the test, go ahead and take a screenshot here. That's screenshot number 1 and number 2 and number 3 and number 4 and number 5, number 6 and number 7 and number 8 and number 9 10. But don't go before you get the homework. The homework is another practice test. Remember, these practice tests are not optional. They're the absolute minimum that you need to prepare for the test. So here's screenshot number 1 and number 2 and number 3 and number 4, number 5, number 6, number 7, 8, 9, and 10. But don't go before you get the answers. Remember, it's not enough just to attempt the homework. It must be done correctly. So here's the answers for the homework. Screenshot number 1. And number 2. And number 3. So remember, if you don't study for this test in the next class, then there's no way you're really going to be able to pass it. You cannot pass a math exam without studying for it. So be sure to get that practice test done for homework. And remember, if you want to get a really good score, an A or a B, then you have to study all the stuff that we did in the previous classes, not just a practice test. But again, this practice test is the absolute minimum that you need to prepare for the exam. So, that said, I'll look forward to seeing you in the next class.